Hello again, physics students. Welcome to number 8 in magnetic fields, coils and solenoids. So we've just done the magnetic field around a current carrying wire, and we used the right hand grip rule to determine its magnetic orientation. And now we're going to deal with what's called the right hand grip solenoid rule. Now what is it? What is a coil and a solenoid, or what is a solenoid? Some people haven't heard of that. Basically, it's where we've taken wire and we make loops of it, and we have a consistent winding, so it doesn't go like that. The wire is wound in a consistent way, and so we have a multitude of loops. We can have a single loop, but then you can have a multitude of loops. And what happens is that the magnetic fields due to that wire, because there's a lot of wire adjacent to a lot of other wire, and each bit of wire is generating its own magnetic field, all those magnetic fields coalesce into a overall magnetic field. And that's why we actually use coils and solenoids, because they can generate a stronger magnetic field. And so they have applications in the real world. For example, when you turn your starter motor on in your car, there's actually a solenoid that drives a bolt that engages the starter motor into the engine and causes it to crank over, and it has to be quite powerful to do that, and a solenoid does it. So we use the right hand grip solenoid rule to not so much determine the magnetic field lines, but to determine which end of the solenoid or the loop is north and which end is south. And so it's a little bit different, and how it basically works is that you now wrap your fingers around the solenoid, and your fingers represent the current direction. So it's now your fingers that represent the current, and so if the current direction is going like that, your thumb always points to the north end of the solenoid. And probably a couple of examples will help us with this. So this is the most simplest solenoid or coil, which is one loop. And so this piece of wire here is generating its own magnetic field. This piece of wire here is generating a magnetic field, but the two must interact. And you end up getting this pattern here, where you have a strong magnetic field in the core and a weak magnetic field outside. And that's an important application as well. And so using the right hand grip rule, let's see if my pen works this time, we can see here that gripping this in such a way, this end here, my thumb would be at this end, so that's the north, and this end here is the south. And that's consistent because the magnetic field lines are going in here, and that's what would happen if this was a bar magnet, and they're coming, let's change colours, the magnetic field lines are going out of this end. So this end is north, this end is south, and that's using a simplest coil. Let's look at some more complicated coils. Okay, and so this is what we mean by this winding. Okay, and so we would have a stronger magnetic field inside the core there. We wrap our right hand fingers in the direction of the current, and the thumb, which is over here, is pointing to the north end of the solenoid, and that tells us the south. And so from knowing the north end, we can then draw the magnetic field, which would be coming out there, into there, coming out, and in, and in. And the important thing that we also need to recognize is that inside we've got a nice strong magnetic field going like that. This is inside, so we just need to recognize that. And we'll get some iron filings out and we'll have a look at this in the lab. Where's some more? Okay, now if we do the cross section through this one, this would be how we would draw it. And so here these are the arrow tail feathers, so the current's going into there. So for you, I think it goes like that, and then these are coming out, and so we'd wrap our fingers around in such a way to get it like that, and then that would determine that this is the north and this is the south, and there's our uniform, nice uniform, strong magnetic field in the core. And just another diagram to show what it means. And this one, just to check that you're okay with this. So here's our current, so that if we get our little pens out, we draw it in red, the current's going, let's try a colour that we might be able to see, yellow, there we go. So the current's going like this on each of these. So wrap our fingers around, that gives us the north. Here the current's going that way, so we wrap our fingers around differently. Here the current's going that way, and here the current's going that way. So in each of these different scenarios we can work out which end is north and which end is south, and it doesn't take much practice as long as we use our right hand. Whoops, what have we got now? Now this is, I've included this diagram, looks like a mess and it's a bit hard to actually think of it in 3 dimensions, but this is just basically a picture of a solenoid getting a little bit clever, because what they've tried to do here is show the individual magnetic fields around each section of the wire, which we learned earlier is circular, and it's this interaction between these adjacent wires that cause these field lines like this. Okay, and the same on this side. So the magnetic fields coalesce into one overall magnetic field. So we're still not, we could still use the right hand grip rule for individual segments of the coil, but we now use the solenoid rule just to determine the overall magnetic field. So you should be able to do question 24 now. And there's a video here of just an electromagnet and a man. You can watch that on the OneNote. And I'm going to make you do a prac on current carrying wires, and then we'll do some more theory videos. Alright, so that should just about do you for this section.